Okay, we are going to discuss now distance vector protocol. Okay, distance vector protocol. Okay, so the distance vector routing, it has basically three steps. So I would like to explain it first through an example. Then we can generally discuss the distance vector routing algorithm. Okay. So basically in step 1, each node computes its complete table. Whatever the information is available, so on date information, the complete table, a complete forwarding table is computed. How it works? Let's see it. Suppose we have a network like this U, V, W, X, Y, Z. These are routers. And these routers are connected through links. For example, ZX, it has a link of 9 meter. This is the weight. Okay, suppose it represents the distance. This is 7, this is 8, it is 4, and it is 4. Okay, so when the routers they are connected through the distance through the data link protocol, we comes to know that when the link is connected, the link start blinking. Okay, so this node becomes to know that it has two neighbors, X and Y. Okay, and this links, it is 2 meter, it is for example 9 meter. So this node at the moment, it only knows about its neighbors when the network is started, when the switch is switched on, when the router is switched on, when its power is on. Okay, so the complete table of the Z at the moment, it will be X is equal to 9 and Y is equal to 2. So this is the at the moment complete table stored in the Z, because the Z only knows at the moment about X and Y. Okay, similarly the Y, it knows at the moment about its neighbors. Okay, so who are the neighbors of Y? The neighbors of Y are Z, V, W, and X. So at the moment, the Y, it knows about its neighbors only. So its complete table is this one. X is at the distance of 7, Z 2, V 4, and W 8. Okay, similarly the table for V, similarly for U table. I didn't mention the table for X and W. Okay, so the first step is that each node has to compute its complete table. Now the second step is that each node broadcasts its complete table to its directly connected neighbors only. Okay, the complete table is not announced to all the nodes, it is only broadcasted to its neighbors, directly connected neighbors. In the link state protocol, each node was broadcasting its link state information to all the nodes, but here it is only sending the complete table, not the only complete the link state information, but the complete table is broadcasted to its neighbors, only direct neighbors. What does it mean? Now suppose this Z node, it has at the moment, the Z node, it has this table, this is the whole table. So the Z will broadcast this table to only its neighbors. Okay, only its neighbors. What does it mean? That Z, it will create a message, and that message will be broadcast address. Its destination address will be 255.255.255. Okay. Whenever the nodes Y, it receives the message with the destination address 255.255, so it is broadcast packet with IP address 255, destination IP address 255. It is broadcast address, so it is for each and every node. So it has to accept it. Accept it means it has to store this information, this table with itself. And second, it has to forward further. it has to forward further. Okay, so as we have discussed that the distance vector router protocol, it broadcasts the completable to only its neighbors. So the packet should not be forwarded further, it should be only sent to its neighbors. Okay, so how to control that this message that is broadcasted by Z, it should be only received by Y, and the Y should not forward it further. So how to control it? So we can control it by how? By setting the TTL value in this message to 1. If the TTL value is set to 1, then we can control this broadcasting, that it will not be forwarded further. It will not be forwarded further. Because if the TTL value is 1, when this message is received at the Y, so the destination address is 255. So it will accept it. That this table information, it will be accepted, it will be processed. We will later we will show you that how it is processed. And since the address is 255, so it should be forwarded further. So when it forward further, so we know that whenever the an IP packet is forwarded further, the TTL value is first decremented and then it is forwarded further. So when the TTL value is decremented in this case, so it will become 0. When it becomes 0, whenever we have discussed that whenever the packet TTL value becomes 0, the packet is discarded, it is not forwarded. We have discussed that the TTL, it is time to loop, okay, in the IP header, and it basically control the movement of data a packet in the network, so that the packet cannot move in the network forever. So okay, so by setting the TTL equal to 1, then we can control this forwarding, that this message will not be sent further. Okay, so but the TTL value in the link state routing protocol, if you know about it, okay, I would like just to show you that in the distance vector in the link state routing protocol, the TTL value was 255. The TTL value was 255 because it was that this link state information, it should be broadcasted to all the nodes. So therefore the TTL value was 255, so that the node, when this node receives a message, so it will decrement the TTL, but the TTL is 255, so it is more than 0, so it will be forwarded further, so it will reach to all the nodes. Okay, so I have just explained to you that in the second step is what? The second step is that the each node broadcasts its complete table to its directly neighbors. So how it is broadcasted to directly neighbors? So we discussed that when the Z node transmit the message, so it will set the TTL value to 1, so that the message is received by its neighbors, and the neighbors, when they forward further, so they have to first decrement the TTL. So when they decrement the TTL, it will become 0. When it becomes 0, so it will be discarded, because whenever a packet value is TTL or less, whenever the packet TTL value is 0 or less than 0, then that packet should be discarded. Okay, we have already discussed it in the IP header. Okay, now when Z transmit this table, this is the complete table at the moment with the Z. So this table will be forwarded to its neighbors only. So neighbors are Y and X. Okay, so when this table is received by Y, by its neighbors, so it will be accepted. Accepting it, its information will be processed. So what does this means? When this information comes to Y, so it means that Y will use this information, that at the node Z, the Z can reach to X. Z node can reach to X. Now Y will know that if Y can reach to Z, Y can reach to Z. So Y at the Y table, the length, the path from Y to Z is 2, and from Z to X in the Z table it is 9. So if Y want to move to Z to X through Z by using this table information, so Y to Z is 2, and z to x is 9. So 2 plus 9, 11. So this is another path. Okay, so at the up to now the y only knows that the x cost is 7, this link. So y doesn't know about this link. When this z table is sent to y, then y comes to know about this link, because this is stored here, that the path from z to x, it is 9. The path from z to x is 9, and this is this link. So y comes to know about it. So y will discuss that whether this is a shorter path or not. So y will compute that, okay, if y want to reach to x through this z, then from y to z it is 2, and from z to x it is 9. So 2 plus 9, 11. So if y wants to move to x through through this link, so this information is 11, this path is 11, and the already path with y to x, it is 7. So the present path is 7, it is less, so the present path will be maintained. This table information of this x, it is of now use, because this path is longer, so the already present path is shorter, so this already present path will be maintained. This already path will be maintained. Okay, now the next information in the table is about y, and y it is itself, y it is itself. Okay, so this information will be not, because the path to y from y, it is 0. So it doesn't have to move through z and then have to move to y. Okay, so this information will not be used, will not be considered. Okay, so you can know that when the y receives this information, so it is processed that whether from this table I can find a shorter path or not. Okay, so this is processed like this way. Okay, so in this case, when the z table is received, so y doesn't find a new path. It found a new path, but this new path is of no use, because it is longer than the existing path. Okay, so the existing path will be maintained, and the other path's value are stored. So now at the moment the y has this table. This is the complete table with the y. Similarly, this operation will be performed at x, but we are not considering x, we are considering only this direction. Okay, now the y wants to transmit this table to its neighbor. What is the table? At the moment, this is the complete table with the y. So it wants to transmit it to its neighbors. So its neighbor are z, x, w, and v. And again, the message will be broadcasted. Its address will be 255. Its source address will be IPY. Its TTL will be 1. Why? Because y wants that this message should be only sent to neighbors and it should not be forwarded further. Okay. Now y will send this table to its neighbors. So who are its neighbors? These are z, x, w, v. Okay, so we are considering that when this information is received by v, so what we will do, you can see that when this table information, it is received by v, so its table is, its destination address is 255, so it means that it is for each and every node, so it will accept it. Accept it means that it will process this information, whether this table, this table, it provides some new information to v or not. Okay, so let's discuss. At the moment, the v has the table, this one, this is the table with the v. Okay, and this is the table that is shared by the y. So let's discuss each entry at the moment. The first entry is x. The v comes to know from this table that we can reach to x if we reach to y. So v to y, the path length is 4. Path length is 4. And from y to x, it is 7, shortest. So 4 plus 7, it becomes 11. So presently the V table, it doesn't have entry for X. V doesn't know about X node. But when this table is shared by Y with V, then V comes to know the about X. So this is the new information. So at the present the V doesn't know about X, but when this Y table is shared with V, then V comes to know about X. So this entry will be added. This entry will be added in the table. X entry is added in the table, and its path is stored 11. Why 11? Because V to Y, it is V to Y is stored in this 4, and from Y to X the shortest path is 7. Okay, so this 7, 4 plus 7, 11. So the path from V to X, it is 11, from V to Y 4, and from Y to X it is 11. So it will be stored. Now we examine the second. The second entry is about Z. This table has contained entry Z. Here the V at the present, it doesn't know about Z. So this is the new information. So it will be accepted. And okay. Now from V to Y it is 4, and from Y to Z it is 2. So 4 plus 2, 6. So it will be added. This entry will be added because this is new entry. This is the new information. Okay, so it is useful. So this entry will be added. Now this third entry, it is V, and this node V is also is itself. So this entry will not be considered. Okay. This is the fourth entry, W. Now we will say that okay, the present value, the present information of W with V is that W is at the 3 distance. It's 3-meter distance. Its value is 3. Its cost is 3 at the present. And V comes to know about from Y table that the cost, if we want to reach to Y, so it is 4, and from Y to W it is 8. So 4 plus 8, 12. So if V node wants to move to W through Y by using this information, then V to Y is 4, and from Y to W is 4, is 8. So it becomes 12, and the already information is 3. So the already present information is less as compared to the information received from Y. So therefore it will be not considered. It is useless. The already present information is less, so it will be maintained. Okay, so you can see that whenever a node receives the complete table from its neighbor, then it is processed. Okay, now this is the complete table with V. Before these two entry, it has only U, W, Y, and now it has this table. So now the we will send this complete table to its neighbors. Okay, now we will transmit this complete table to its neighbor. So its neighbor are Y, W, and okay. So now we are sending the data to its neighbors. Okay, now when we transmit this table to the U, so U will update its table. We are only considering these nodes, the rest are not. The similar operation will be performed by WX as well. Okay, so suppose this U receives this table. When this receives, so it will accept it. Accept it means that the U node, it will process this information, that whether from this table the U node can get the new information or not. Okay, so each entry will be examined at the moment. So first this entry will be examined. This is U, and this node is itself U, so this entry will not be considered because the path from U to U is 0. Okay, so this entry will not be considered. Second entry, it is about W. At the present, the U knows that the cost from U to W is 3. It is how much? 3. And if U wants to use this information, then U to V, u to v is 7, u to v is 7, and from v to w it is 3. So 7 plus 3 10. So if you wants to use this information, then if you wants to reach to w through v, then this path length is 10. Why? From u to v it is 7, and from v to w it is 3. So 7 plus 3 10, and the present information is 3. So it means that this new information, it is useless, it will not be considered. The present value is minimum, so the present value is stored. Okay, the next entry in the table is for y. For y, presently the u, it doesn't know about y, so this y is a new entry, is a new information, so it will be accepted. But what is its distance? From u to v it is 7, and from v to y it is 4. So 7 plus 4 11, 7 plus 4 11. So it means that u can reach to y through v, through node v. And what should be the cost? Its cost should be u to v is 7, and v to y is 4. 7 plus 4 11. So u to y cost, it will becomes 11. So this is the new information. Before this, the u doesn't know about the y, but now it comes to now. Similarly, the third entry, it is about x. Presently, the u knows about x. Okay, and what is its cost? Its cost is 5. So if you wants to use this information, then u to v is 7, and from v to x is 11. 7 plus 11 18, and the present cost is 5. So the present cost is minimum, so the present cost will be maintained, and this new information, it is useless, it will not be considered. Okay, similarly the fourth entry will be considered. You can see, presently the u node, it doesn't know about z, but from this v table it comes to know about z. And what is the path? So from u to v it is 7, and from v to z the shortest path is 6. 7 plus 6 13. So the new path from u to z, it will be 13, and this entry will be brought itself. Okay, so this is now the complete table. So you can say now, in this iterative approach, the nodes come to know about the table. Okay, so you know that at the first moment, each node has the link state information of its neighbors, only its neighbors. It has complete table about its neighbors only. The complete table contain only its neighbor. But when the nodes transmit the message to its neighbors, then the nodes update their table, then the nodes come to know about the other nodes, So in this way, if each node transmit its complete table to only its neighbors, then each node will come to know about the whole network topology. Okay, so this approach, this is called distance vector routing protocol. Okay, and this is the distance vector routing protocol working. Okay, so we have discussed it, and now we are going to discuss it through in more detail. Distance vector routing protocol, it is uses Bellman-Ford equation. What does Bellman-Ford equation means? This is the Bellman-Ford equation. Okay, suppose dxy, it represents the shortest path from x to y. Okay, so we are going to explain this equation. What does it mean? So suppose we are considering node u to z. This is the node u. So node u wants to compute shortest path from u to z. So duz means shortest path from u to z. So you know that in distance vector routing protocol, each neighbor sends its complete table to its neighbors. So v will receive the complete table from v, from x, and from w. Okay, so when this when u receives the complete table from v, from x, from w, then it will update its information. How it will be updated? You can see that when it receives the information from v, so the cost from u to v, it is 2, and the cost when the v sends the complete table, so we will have the its information from v to z shortest path. It will be stored in the complete table. Suppose it is dvz, dvz, and dvz is, suppose it is at the moment 5. So it means that if u wants to reach to z through v, then the path will be u to v 3, and from v to z it is 5. So the cost will become cuv plus dvz. So 2 plus 5, it becomes 7. Similarly, if u receives the complete table from w, so this w table, it will contain the information to node z. Suppose from w to z the shortest path is 3. Shortest path is 3. So if u wants to reach to z through w, so u to w is 5. Cost from u to x, u to w, it is 5, and from w to z it is 3. So 5 plus 3, 8. Similarly, the u will receive the complete table from x. So if x has an entry in its table to z, the shortest path from x to z, and suppose this path is 3, dz to 3. So if u wants to consider the path this one through this neighbor to z, then u to x is 1, and x to z is 3. So 1 plus 3, 4. So you can know that the u node, it comes to know about z from its 3 neighbor v with this cost, w with this cost, and x with this cost. So it will select the one neighbor, which has the lowest cost, which has the minimum cost. So minimum cost is 2 plus 5, 7, 1 plus 3, 4, 5 plus 3, 8. So 1 plus 3 is minimum, and 1 plus 3 is the cost of u to x and x to z. So it will consider that the path from u to z, the shortest path from u to z is through u to x and x to z. And you can know that u to x, it is directly known 1, and from x to z it relies on the table of x. That the shortest path from x to z is 3. So it relies on the table information of the x. So this is called Bellman-Ford equation. What does it mean? That if the path from x to z is shortest, and u to x and x to z is also shortest, then it means that from u to z is also shortest. This is called Bellman-Ford equation. Okay, so in the last example, if you do remember, so we were only discussing that the table information is received from one neighbor. If the table information is received from z, from x, from v, then the table information of all are evaluated. Okay, so the minimum entry will be maintained. Okay, so this is called the Bellman-Ford equation. That if a node x want to reach to y, okay, and it has the neighbors v, these are the neighbors, and from v neighbors, the set of v neighbors, it receives the path toward y. So it will use it will select the minimum among the neighbors. Okay, so this is explained through this example. Okay, so we have discussed this algorithm, and I think it is much clear. Okay, so the distance vector algorithm, the key idea is that from time to time each node sends its own distance vector estimate to neighbors. You can see that each node it sends its complete table. Does it transmitted to its y, y transmitted to v, y transmitted to u. So in this state, from time to time, the nodes, they are transmitting their complete table. So ultimately, then each node will come to know about the whole network topology. Okay. When x receives any new distance vector estimate from neighbor, it updates its own distance vector using Bellman-Ford equation. As I have explained to you, that when a node, for example, y receives the complete table from z, then it updates its table. Similarly, when v receives the complete table from y, it updates its own table. Okay. Okay. So under minor and natural condition, the estimate it converges. So we can see that after some time, then all nodes, it will come to know about the whole network topology. Convergence means when the each node becomes to know about the whole network topology. This is called convergence time. So convergence time in distance vector, it is longer. Why? Because z will transmit to y, y will update its table, and then y will transmit to v, and then we will update, and then so it will take time. But in linked state information, each node was sending its complete linked information to all the nodes, so all the nodes come to know about the whole network topology at once. So the convergence time at the linked state of the protocol was very less. Okay. So this is the Bellman-Ford equation that we have explained. So distance vector routing protocol, it is iterative, why, and asynchronous, because each local iteration caused by local link cost change. That is, when a node transmit its complete table to its neighbor, when will it transmit? After some time, for example, after 5 seconds. After every 5 seconds, a node will transmit its complete table to its neighbor, if there is no change in the table. But if there is change in the table, for example, when y table, for example, when v table receives this information, so the v table is changed. The v table is changed. So when the v table is changed, so it will be transmitted immediately. It will not wait up to 5 seconds. But in this case, when y receives the information from z, then the z table is not changed. So it will transmit this table to its neighbor after 5 seconds. But when v receives this information, so it is updated, the table is updated. Whenever it has the updated information, it will immediately send to its neighbor. It will not wait for 5 seconds. Okay. So whenever there is a change in the update, then the local link cost change, then it sends the information to other nodes. It is distributed. Why? Each node notify only its neighbors. It is distributed in nature. Okay, and then the neighbor compute the table, and then the neighbor notify their neighbors if necessary. If necessary means that if there is change in the table, for example, you can see, then when y receives the information from z, then there is no change in this y table, so y will transmit its information after 5 seconds. But when v receive the information, the v table is changed. When v table is changed, so it will immediately transmit this table to its neighbors. Okay. So we have discussed it. So each node, it is waiting for change, and when there is change, it recomputes the estimate, and then it notifies the neighbors. Okay. So this is another example of distance vector routing protocol, and we will discuss it through in the next video. Okay.